for joining us at this occasion at the inauguration of Professor Bernardo Rodrigues. My name is Professor Bernardo Erasmus. I'm the Dean of the Faculty of Natural and Agricultural Sciences, and I'll be managing the program tonight. It's a very simple program. I will introduce Professor Flavia Senkubuge to formally introduce and welcome our inaugurating professor, and then it is for the man of the moment, Professor Rodrigues himself, to deliver his inaugural address. Professor Flavia Senkubuge was appointed as the Acting Vice Principal for Student Life in August of this year. She earned her undergraduate and postgraduate qualifications from the University of Pretoria, and she's a specialist in public health medicine with a PhD in public health and an MBA from the Edinburgh Business School. In addition to a Master of Medicine and a PhD, she holds a fellowship of the College of Public Health Medicine. She joined the university in 2011, and here she lectured at both undergraduate and postgraduate level, and her research is mostly on health policy and the management of health systems and how they can be strengthened. Professor Senkubuge is well respected on the African continent and globally. She's currently the immediate president of the College of Medicine of South Africa. Her election was historic in so many ways, as she is the first black woman and only the third woman in the CMSA's 66-year history to hold this position. She's a fellow of the prestigious Kofi Annan Global Health Leadership Program, and in 2022, the Harvard Public Health recognized Professor Senkubuge as one of the 25 standout voices in public health. It gives me great pleasure to introduce Professor Flavia Senkubuge to introduce our inaugurating professor, Professor Senkubuge.
Thank you very much, Professor Bernardo Erasmus, and you're welcome to clap. So, distinguished guests, and in the interest, because we are inaugurating really just such a wonderful scholar, I did ask him that, how do you say good evening? And he said to me that you say boa tarde. So I will start with saying boa tarde, because I know that there are so many people who are joining us all the way from Angola as well, who are online. And so I want to say good evening to all of you, and on behalf of the Senate of the University of Pretoria, it's a great honor and privilege for me to welcome you all to this inaugural lecture of Professor Bernardo Rodrigues of the Department of Mathematics and Applied Mathematics at the University of Pretoria. And I really want to extend a special welcome, firstly, to our very honored guest, to you, Prof. Rodrigues, and I also want to really extend a word of welcome. It will be remiss of me not to mention that, in fact, for somebody to achieve this great honor, they don't achieve it alone, and there's always family behind them, and I really want to welcome you very warmly, Mrs. Veronica Rodrigues, the wife of Prof. Rodrigues, and also their son, Bernardo Rodrigues, as well. And I want to welcome as well the colleagues of the Executive and the Dean of Faculty of Natural and Agricultural Sciences, Prof. Bernardo Erasmus. I don't know where he got that bio from, but we'll talk about it afterwards. And I want to say thank you for that very warm welcome. And I also want to really recognize the Deputy Deans of this faculty, and the whole team who are here of the Faculty of Natural and Agricultural Sciences. And I also want to recognize all the friends, all the mentors, the peers, the colleagues, and of course, Prof. Rodrigues' students, and also our students here at the faculty. And I do, and must say as well that it is also important to mention that in the audience and also online, we do have people who have really contributed to Prof. Rodrigues' career and who have offered up their time to share with us in this occasion. And I really want to warmly welcome you and recognize you in a special way. And to all of you in the audience, it's just such a great honor to have you here this evening. And you will excuse me, colleagues, because this is really a momentous occasion. And I will take my time in reading Professor Rodrigues' bio, because really this is something that is a pinnacle in any academic's career. There's an old age African proverb that loosely translated in English that says, success comes to those who wake up, who work, and who dream of greatness. And so today, as we celebrate this wonderful occasion of a colleague and an academic, we really want to say, Professor Rodrigues, that you have woken up, you have slept, and you really have dreamt of this particular success this evening. And we really want to recognize you and your circle, and also the fact that you have all of you, because really this kind of achievement is usually done in teamwork, and to say to you and colleagues who have assisted you to be here this evening, that you have come full circle, and as a university, we're so deeply proud of you. An inaugural address, colleagues, is a very auspicious occasion, as I said, and it's an event in an academic's life which is extremely special. It is marked by rite, by ritual and tradition, and that's why you see us wearing all our garb this evening. And so senior academics are typically required to deliver an inaugural lecture when they are promoted to full professorship, or sometimes even when they are appointed into a position of academic leadership. And after the graduation ceremony, at which a doctoral degree is conferred, you may even give an inaugural address during that time. And so again, as I said, it's really quite memorable and quite special. And each time an esteemed academic delivers an inaugural address, we have an opportunity as a university and also our faculties to really showcase, yes, the scholarly role models that we have in this university, but at the same time, it really is a moment of pause and reflection to really showcase excellence here at the university and also in the academic space. It's an indelible part of our proud culture and heritage as an institution of higher learning, but also, I dare say, in our academic fraternity as well. And so it is a moment for an individual's academic, and as an academic, to really take a moment and reflect, and not only reflect, Professor Rodrigues, I hope you'll also rejoice this evening and revel really at the results of the hard work that you have put in and the dedication that you've put in to make sure that you achieve this particular enormous and wonderful achievement. And so this moment and this evening really belongs to you, so please don't feel shy when we overly celebrate you and fully recognize your entire achievement. And really, colleagues, for those of you who find yourselves in the audience, at times like these, it's really a moment to take in the full magnitude of what you will hear this evening, but also to really journey with Professor Rodrigues as he shares with us what it took for him to become a full professor. It's really hours of sacrifice. It's moments that are spent away from family, from loved ones. It's long, grueling hours spent studying academic material, traveling, completing many, many commitments as well in order for you to advance, yes, the academic profession, but also the academic project. And so Professor Rodrigues is a mathematician, but he's also a man of numerous talents, which include writing as well. He's a committed academic who has not only made a great impact in his field of mathematics, but also in writing as well, as I will talk a little bit later on. He started his undergraduate studies in mathematics and education in Cuba in 1991, and then he proceeded to earn a BSc honors, a master's, and a PhD in mathematics between 1997 and 2002 at what was then called the University of Natal Pietermaritzburg campus. And there at the University of Natal Pietermaritzburg campus, he also started his career as a temporary lecturer and also a postdoctoral researcher. After teaching maths at different universities in Angola in 2004, he returned to KwaZulu-Natal and he steadily worked his way up the academic ranks in the School of Mathematics, Statistics, and also Computer Science at the University of KwaZulu-Natal. He joined the University of Pretoria as an associate professor in the Department of Mathematics and Applied Mathematics in January 2020, and he was recognized for his stellar work and was subsequently then promoted to professorship in January this year. Professor Rodrigues' research interests are in the theory of finite groups, modular representation theory, combinational design theory, the links of these to algebraic coding theory, algebraic graph theory, and also permutation decoding. He also works on problems that relate to the classification of axial algebras from the sporadic simple groups and also groups of three transportations, and most recently, he has started work on determining binary self-dual codes which admit rank 3 groups as permutation groups of automorphisms. I believe that colleagues, all of us here this evening, are able to appreciate the extent of excellence that Professor Rodrigues has achieved. And what is really particularly significant is that through his work, Professor Rodrigues has been able to make contributions towards an understanding the dynamics of epidemiological disease transmission. And I must say, Professor Rodrigues, that made me very delighted as a public health medicine specialist. And with this, he has been able to use classical methods of difference equations and networks in graph theory. And this is transdisciplinary research, I must say, colleagues, at its best. I do want to quote Shanktula Devi, who was an Indian-born mental calculator and writer popularly known as the human computer, and whose talent earned her a place in 1982 edition of the Guinness World Book of Records, and who once said that, what is mathematics? It is only a systematic effort of solving puzzles that are posed by nature. And so, as I stated earlier on, Professor Rodrigues is really, yes, an expert in mathematics, but he is also a prolific scholar and a prolific writer who has authored 4 chapters in books, 77 articles in scientific journals, and nearly a dozen articles in the popular press. He has also refereed 35 journals, and one of the things that he did was to be the managing editor as well for the journal Africa Mathematica between 2013 and 2018, and he has since served as its deputy editor. The list of his lectures, his seminars, and visiting professorships is really endless, which takes him from Potchefstroom in South Africa all the way to where we're playing rugby in Paris, and also to Auckland, to Angola, to Namibia, to Naples, Kampala, to Cambridge, Croatia. And so it is very clear that this is a stellar academic recognized not only here nationally, but also regionally and also internationally in his field. As a lecturer, Professor Rodrigues has taught mathematics at various levels and to a wide range of students in universities in Angola, in Cuba, in South Africa, and with class sizes ranging, you have to hear this, from 35 all the way to 500. You need to give us the secret of how you teach mathematics, Professor Rodrigues, to 500 people. And so he's also successfully supervised 13 honors projects to completion, as well as 11 master's students, 5 doctorates, and 4 postdocs. At present, Professor Rodrigues has got 4 candidates who are conducting their master's and doctoral research under his supervision. Professor Rodrigues' reputation really precedes him, colleagues. He has received numerous honors, grants, and awards, including the Erasmus Mundi Plus Scholar in Croatia, and this was in 2016, 2018, and this year in 2023. He has also received the Isaac Newton Institute Invitational Program, and this was in 2020 and 2022. He is also a Fulbright Scholar to Michigan, and that was in 2017. And his current rating with the National Research Fund, which is NRF, is C1. And so this evening, Professor Rodrigues' title of his expert lecture is called Algebraic Coding Theory, Pure Mathematics Close to Practical Applications. And so this is particularly relevant to our institution and also the vision to ensure that we are a leading research-intensive university, but also recognized for our quality, but particularly as well for our transdisciplinarity in the way that we work. We have a recognition that the reality of the problems that we face are both complex and wicked. And so in essence, we cannot always just sit in our own silos, but we really have to work across our different spaces and our different fraternities. And so in reality, colleagues, there's been significant interaction then between all the different groups that Professor Rodrigues has worked with, and he's made critically significant impact, not only in his own academic endeavor, but really an impact in society as well. The continuous development and increasing relevance of digital data utilization make algebraic coding theory a research field of primary interest that needs constant study and updates to keep up with the technological demands of modern society. And so in his lecture, Professor Rodrigues will demonstrate that algebra and coding theory are intertwined by providing some examples of the interplay of coding theory, which covers several topics and is widely studied as an interdisciplinary space. And the subjects will involve techniques from computer science, engineering, information theory, and mathematics. Professor Rodrigues will also try to illustrate some of the links of the subject to areas not immediately seen to relate to groups, and in turn illustrate that research areas in pure mathematics, such as algebraic coding theory, and very close to practical applications. So this evening, colleagues, we are really privileged to listen to a stellar scholar who is a world-renowned mathematician and whom we are privileged as a university to call one of our own. And so as we say, Professor Rodrigues in South Africa, halala, which means congratulations, halala, and please enjoy your evening. Over to you.
Indeed, I am without words. Professor Senkubuke, I do not know where you found the energy to say such kind words. I'm greatly delighted, and I thank you very much for this. And I hope that my lecture will live up to your expectations. To the Dean, Professor Erasmus, the Acting HOD, Professor Shapwania, colleagues, friends, and family. Good evening and welcome to this, which is a day that will stay in our memories as a celebration of a milestone. Allow me to take this opportunity to thank those in the university who have made the decisions that led to this present act. I thank those of you in the audience, those attending virtually, and most particularly I thank Laurel and Marie for the tremendous amount of work you've put together so that this occasion would come to being. I will dedicate this address to my family, to those colleagues who have passed on and are no longer with us, those who dearly held my hand and made me realize how important it was to ask a very trivial question: why? To those colleagues of ours who have passed, and most especially to my late parents, I'd like to dedicate this lecture. And I thank you all very much. The title of the lecture that I will give, it is one that wants to convey a relationship that exists between things that we often think very little of, but they are very important in our daily lives. And these are aspects related to the interplay between what we communicate and how this communication flows. As the title of my lecture reads, Algebraic Coding Theory Towards an Error-Free Communication System. What would I like to tell you? I'd like to sort of guide you and ask you to be with me, to sort of give you an idea of information theory as a highway to communication. And in telling you about information theory, I'd like to also uncover how communication takes place. And by so doing, let me first tell you something about mathematicians. There is a quote by Paul Erdős that says, a mathematician is what you say, a device for turning coffee into theorems. So people just sit around, play with things, and come with ideas and call them theorems. Well, but there is even more. If you ask mathematicians what they do, the answer that they will always give you is that they think. They think about difficult and unusual problems. They do not think about ordinary problems. They just write down the answers. And that's what we do. But there is more to it than just writing answers. There is also the issue, do we do anything at all? Well, one of the endearing things about mathematicians, as my dear colleague would say when he sat down with me in KwaZulu-Natal at a tea time, he'd say, let's think of something and prove it. Yet, we weren't doing much work because all that we were doing were things that are passionate to us. They are things that we call hobbies. And then we don't do that much work. We do that to try to avoid doing any work at all. What else? Well, you know, we all became mathematicians for the same reason. We were lazy. And this is why we are mathematicians. We can't fix a chair. We can't even put a light bulb. So, we're really lazy. Okay, so, much to what mathematicians do, what then are we trying to do in today's lecture? Well, when one thinks of information, one needs to immediately think of the forefathers of information. Claude Shannon, in a seminal paper, A Mathematical Theory of Communications, he said that the fundamental problem of communication is that of reproducing at one point either exactly or approximately a message selected at another point. Well, what does that mean? What it does mean is he predicts that for any given degree of noise, I'll tell you what that is. Communication of noise communication of a channel, of a communication channel, it is possible to communicate discrete data, in other words, digital information, nearly error-free up to a maximum rate through the channel. Well, what Shannon's article did was to lay out what the pillars of communications are. One would have an information source that produces a message. a transmitter that operates on the message to create a signal, which can then be sent through a channel. A channel which is a medium, really, over which the signal carrying the information that composes the message is sent. Well, a receiver, which transforms the signal back into the message intended for delivery. But what else does Shannon say? A destination which can be a person or a machine for whom or which the message is intended. It is also developed, he also developed the concept of information entropy, and it's known to have introduced the idea of redundancy and introduced the term bit. What do we mean when we say Shannon has devised this protocol? Well, if you see in this diagram, we have what is called an information source and a message being passed through a transmitter and a signal being received. And there is then in between a noise that is carried in this information. And then that message is sent as a received signal to a receiver, who then notices the message and understands it. And this message then would have reached its destination. Okay, what then is information theory? Information theory is subdivided in two categories: coding theory and cryptography. The business with coding theory is that of correcting messages, while the business of cryptography is to keep secret. It's to send secret messages, and secret in the sense that there could be someone listening, and this someone listening could be someone who would tamper with the message, and therefore the message needs to be protected, and therefore having the need for secrecy. But that's not all that these two subjects do. Coding theory is known to have been used in CD players, disk drives, photographs from the outer space, digital radio, and possibly cloud storage as we know it now. Well, secret messages, we do electronic banking, we use credit cards online. We do authentication of our signatures. And for secrecy's sake, there is also the aspect of military communication, which is not known to the public. Now, how does the mathematics come to that? Well, cryptography is concerned with transmission of secret or sensitive message. And that is something that could be used for the benefit of a party. Crypto has two strands. One of the good guys, which must devise ever more sophisticated ciphers to cope with the ever-increasing expertise and computing power of the bad guys. This means that the good must put themselves in the role of the bad and subject their proposed encryption scheme to the most powerful code cracking techniques. This shows that the history of cryptography is a continual battle between the parties conveniently referred to as good and bad. The bad will usually be one step ahead of the good guys. And the bad are those that we call the hackers. And things like what happened on the internet as fraud will never go away because we will always have the bad guys one step ahead. So it is important for the good to be a step further. And therefore, it's important for the good to bring innovations into the process. Now, how about coding theory? Coding theory is, to some extent, similar to cryptography, but it has three important differences. The enemy now is not a person anymore. It is not an organization, but it's nature. The enemy acts not by making improper use of the message, but by distorting it, so that even the intended receiver can no longer understand its content. The mathematics of cryptography is number theory, statistics, computational complexity, and more recently, algebraic geometry. Coding theory makes use of linear algebra, Boolean algebra, polynomial rings, finite fields, and combinatorics, just to mention a few. These disciplines would certainly be an excellent refutation to our dictum. Beautiful mathematics and useful mathematics are distinct. Well, we can see that in today's life, this is not necessarily the case. All right, now, nature can distort communication in several ways. You could be at a party and cross-talking with someone on the other side and not being heard. You could be making a telephone call, and a crackle on the line may make communication unfeasible. Or there could be solar flares interfering with satellite-to-earth communication, things like this. To take a temporal rather than a spatial communication channel, information stored in a computer can over time be corrupted by stray half particles. Well, physical protection of the channel has only limited feasibility, especially if the channel is interplanetary space. So some methods must be found of enhancing the message sent so that even if distorted transmission, the receiver is able to reconstruct the original message accurately. Well, as I said, what is then coding theory? Coding theory is an application of information theory, which is critical for communication and fault tolerance, information storage and processing. A code designed based on a well-defined set of specifications and protects the information only to the type and number of errors prescribed in this design. A good code has the following features. It adds a minimum amount of redundancy to the original message. Efficient decoding and decoding schemes for the code exist. This means that information is easily mapped and extracted from a code word. Having given you this, then let me give you the essential idea. Suppose you have two words that you would like to send in a channel, one being yes and the other being no. Okay, you send one and receive 0. How do you know what was sent? You, at this stage, do not know if an error has taken place. So what then do you have to do? You then have to add redundancy to the message. And as you can see, at the second stage, you have yes with 1 and 1, and no with 0 and 0. Now, if you suppose 0, 0, for example, is received, what are the possibilities then? Then either 0, 0 or 1, 1 has been sent. So, again, what have you been able to do? You have been able to only detect, but you cannot correct an error. So you add, yet again, some more redundancy. And yes will now be written as 1, 1, 1, and no will be written as 0, 0, 0. Suppose now that 1, 0, 1 is received, then what is the likely message to have been sent? Now what happens? We go and compare in the set of messages that we have sent. We are saying that we have received 1, 0, 1. What are the likely messages to have been sent? If you compare the two between yes and no, you will notice that no has 3 zeros and yes has 3 ones. The number of ones in the received, it's more than the number of zeros. So what is likely that might have happened? That 0 that is in between 1 and 1 is then in error. And therefore, the most likely message to have been sent was 1, 1, 1. And this then, you would effectively correct this message to a yes. Okay. Under the assumption that at most one error has occurred. Well, then There are other possibilities. As if you notice, what I have highlighted in red are the messages, and the ones highlighted in blue are the possibilities. Now, this code will consist of the red parts, and whenever one has a code of this nature, it's called a perfect code. And there are families of such codes, and those codes have been designed to correct a single error. Every triple has only one digit different from a code word. If you look at 00 and 11 and compare to any one such, you'll notice, for example, that in the case of 000, you have 001, then you are likely to have got 00 cent, because there is only just one difference with 00 and 0. But if you see that you have received 110, then there are more ones there, and therefore the likely message to have been sent was 111 in the set of messages that you have got. If you look closely to this diagram, you will notice that there is a possibility that an error has occurred. When you go to the second part of the diagram, you will see that this message source encodes a message, and there is a channel that perturbs that message by introducing an error. And then a received vector will have changed. The brackets represent either of the possibilities. And the estimate will be that 111, which it's 1, or 000 would have been sent. So in that way, then, the channel would have been able to correct an error. Now, these errors, as they occur with certain probability. Each digit, as it is sent, can be transformed. And now we want to understand how many errors, or which is the probability that an error has occurred in any one of the digits that has been sent. And one can do this calculation by taking this formula, which is below, which I will not read for you in the interest of time. So then, if in that example we have 0 and we convert it into triple zeros, and 1 and convert it into triple one, we are able to determine the probability that each one of those digits has arrived with an error. And we are then able to determine how effective is the process of correcting those errors. Okay. With this being said, suppose you have this nice idea of you being at headquarters and X being a lost spy of yours. Well, let's think of James Bond and a place where James Bond needs to get to. But there is an interval between James Bond and the headquarters. What if there is enemy soil and James Bond has to reach his destination? But in between, he needs to follow a map, and that map is coded north, east, west, south. How does headquarters direct James Bond to get to the place where he must get? Let's see. Let's work with James Bond. So what's happening here is that here we are, at this stage here, we are indicating to X to reach precisely headquarters. How do we tell X to do that? Well, suppose we code the objects north, 00, east, 01, west, 10, and south, 11. Well, as it is, this code does not allow you to make a mistake. But what if you didn't understand what was sent to you? 01, which was told to you, you may have perceived it as 10. You would have gone to the wrong direction. You would have made a mistake. Suppose that that land is full of landmines. You are now at risk. Suppose there are crocodiles. You are now again at risk. What then should you do? You should be allowed to make mistakes. And if you make those mistakes, you should be allowed to correct them. This is, in a way, a role of error detecting and error correcting. So, James is being told, mind you, my colleague James in the audience, at this point I'm referring to James Bond. Well, 00 now, you have seen has been increased to 000. All right? It's not 007. It's 000 this case. So now what we have is 011 for east, and as we go below, we have increased on the digits. How did we increase these digits? Well, if you look at the two digits, when you add them, that addition you want to divide and find the remainder. So if the remainder is 1, then you increase by 1. If the remainder is 1 plus 1 divided by 2, the remainder, 1 plus 1 is 2 divided by 2, the remainder is 0, then you put 0. Well, some people say that 1 plus 1 cannot be 0. Well, in this instance, 1 plus 1 is indeed 0. Well, and it's important then to know a little bit about your algebra. And this is where the algebra comes in again. So what happens now, we have 1, my eyesight is betraying me. I have 1, 1, 0 for south. And what happened there is when you add the first two digits, 1 and 1, you have a 2. Divide by 2, the remainder is 0, so you put a 0 there. This is what we do. Okay, so next then, we would have given instructions to James Bond to get to where he needs to go. With that first idea of increasing, we were able to tell him that he can make a mistake. He will be able then, in this case, to get to the place where he wants to. But he does not get there with C2. He will only possibly get there with C3. What happens is we added 2 extra zeros, and we added the message got added with 2 bits at the end. And now what happens? Let's look at it. Suppose what we got is this object over here. And what then happens? This is what we've received. This is the message that he received. And how close can we correct that? If you look at n and you compare with the previous case, you would have realized that where are you much closer? You're much closer here, so this would be n, possibly. But you could also have said it's e. You could simply also have said it's s. Any one such options are possible. If you look at this, suppose this is received, then any one of those 3 options is possible. Suppose then in the end that you have added this bit, which is then adding redundancy, as I said initially, and suppose this is what you have received. What is the likely letter or direction to have been sent to you? Well, with a careful deduction, we can quickly realize that n differs in 2 places with the received message. E differs in exactly, I think my eyes again playing tricks on me, in 1, and W differs in 3, and S differs in 4 places. So what is the likely then object to have been sent? So this, which you have received, will be then clearly decoded as that. And in this way, what happens is you have extended your message into 5 digits. There are 2 messages, okay, which are there. And if you notice that the smallest number that will be here of different places is 3, and therefore the difference between any 2 different words or messages will be 3. So that is the shortest that you can get. Well, we all know about books, and we all know that books are coded. Well then, coding the books in this way, we can write the ISBN, International Standard Book Number, as X1 for language, and X2, X3 for the publisher, and all the way from X4 to X9 will be a number assigned by the publisher, and X10 then can be calculated in this way. You sum all the digits and see if they are 0 when you divide by 11. And then the 10th digit will be the addition of the 9s and calculate upon division by 11 and see what the result is going to be. this code is allowed to detect and correct one digit, and is also allowed to detect transposition of two digits. With that, let me give you an example. Sorry. Oh, right here. Oh dear, this is a real absent professor. I apologize. I've been having the second pair of eyes next to me, and I did not notice that they were there. I really apologize for this. Well, this looks much better. The only difference is that I don't look like Bernardo anymore. Well, then, what happens in this case is that, as I said, the first part, it's giving you the language, and X2 and X3 is giving you the publisher. Let's see what we get there then. Well, X1 is it's written as 0, therefore we're going to get that this book is published in English, and X2 and X3 give you the publisher, which is Addison Wesley, and all these digits will be coded in this way. When you have done the sum of these and divide by, when you've done the complete sum of the digits from X1 up to X9, you get 131. You divide by 11, you get then that this X10, which we had calculated here, which we said how it's calculated here, can then be written as X. So this then becomes the check digit in this book. And we now know which book it is, who published it, and in which serial number it is. So with these ideas, I hope to have given you a flair of what communication and error correction is. Well, airlines have also an idea of determining when a certain ticket is faked by someone. That is done by having a check digit and having a number which is congruent, mode 7. Credit cards also have check digits. That's why they are safe. There is a mathematics behind this. Well, having said this to you, then let me remind you that for those of you who do not remember what a CD looks like, this is how a CD looks like. There are people in the audience who have been born and got here when the CDs weren't there anymore. I thought I should rather illustrate the idea of what a CD looks like, because nowadays everything is done on storage, so we don't understand what CDs are. So this is more or less like what a CD used to look like. So CDs were given, once one had a CD, if a CD had some track incorrect, that had a built-in mechanism that would allow for correction of errors. Those were so-called burst errors. And Reed-Solomon codes were those that were implemented in CDs. Nowadays, digital TV makes use of these kinds of codes. And these were also used when pictures were sent from the outer space, going into Mars, Jupiter, and Saturn. Well, most people in the audience, not all, have Facebook. Now, what happens? Facebook nowadays, it is estimated that something of the order of 300 million photos are stored on Facebook every day. Can you imagine the sheer amount of information that we are storing? What if those are corrupted? How do we recover those? What is the mathematics behind this? Is there any? Well, this, what I am telling you, it's also a mathematics of compression and decompression, of storage and recovering. So, what more can I tell you? Well, the forefathers again come in, and Richard Hamming was the first person to basically create the idea of, if a message is sent in error, how do you correct it? And if there is an error, how do you detect it? So with Richard Hamming having brought these, he has basically opened the possibility for our knowledge on how we correct errors and whether or not we will have information that is complete. Now, in this pathway, I have thought of just highlighting for you what Richard is known for. He's known for introducing the idea of Hamming codes Hamming distance, and Hamming metric. In fact, when Richard Hamming introduced the idea of error-correcting code, it is believed in the theory that in 1948, Shannon postulated the theory of communication. However, Richard Hamming was already working on the problem as early as 1947. It so happened that his paper was published in 1950. It could be conceivable that both would have been the forefathers of this theory. But people in coding theory have now settled with the idea that Shannon is the creator of information theory. Okay, so then what happened in that, what we did, what we are discussing here is information transmission through a channel using code words of a fixed length. We have an alphabet, so zeros and ones, and we have an encoder that encodes the message in blocks of given length. And what happens too is that redundancy is added to the message so that the message is protected. In fact, the whole idea of redundancy is to protect the actual message that you're sending. Now, having done that, then we need to sort of understand what does it mean to have a code. So what does a code do? The code will measure the efficiency of sending messages. Now, what happens is that set of objects that you send, the objects that are sent are called code words. There is then a set of objects which is called a code. And a block code will have messages of given length over a given alphabet, and there'll be that many messages which are in here called set of M messages. Now, what more can I tell you is one can now pick on the mathematics of these objects and say, suppose you have a metric space and you have an encoding map, and you have then, for those of you who are not mathematicians in the audience, in both online and now, and in presence, I apologize for introducing these ideas, but I must warn you that you signed up to come to a talk by a mathematician. And this is the part where you will have to endure a bit of mathematics. All right? So then we have a metric space, we have a function that is sending the set A to a set S. Your alphabet is being then now encoded. So what happens is you have this object in your set C. This is then a code word. In other words, it's a message. So what we do really, we're doing point-to-point communication, which is the classical setup. And there is this object, which is the one that consists of all words. And when do you know that two messages are different? So what you do then, you look at the number of positions in which they disagree and the number of places where they differ, as you saw in the examples that I've given you. This is called the distance. And look for the smallest such a distance. That is called the minimum distance. And that probability which I told you is the probability which is embedded into a binary symmetric channel. Binary because you are working only with 0 ones. It doesn't mean to say that this is the only possibility. No, there are many more. So since this is a talk to a general audience and a talk to mathematicians, let's then sort of look at what happens here. If I gave you a set C, which consists of C0, C1, up to C3, and these were the messages that you're sending, you're trying to look for the smallest such values. In other words, those messages are much closer to the original than any other. So the smallest the distance, the better for you. So the smallest distance in this case here would be 3. And this then means that this code has length 5 and 6, and the smallest distance or the smallest difference between any two different messages is that 3. So with that, then, one could ask the question, how many errors can a code correct, and how many can it detect? If you have a code of length n, and which consists of k messages of distance d, then that code C can correct d minus 1 over 2, and you take the integer part of it, and it can detect precisely d minus 1 errors. So how important it is to have this. Remember, what one has done is to have a message which you put in new digits, which is redundant. You made the message long, which then means it is going to be harder to send. But you want to send as many as you need, but you want to make as little errors as possible. I think you're asking for too much here. And this is the reason why we're saying there are some combinatorics involved in here. And as Professor Senkubuke told you, there was some interplay into many disciplines, and this is one part where I would like to highlight that. What we want is we don't want the word length to be too large. Why? Because long words will take longer to transmit. We would like the number of code words to be reasonably large because we want to send as many messages as we can. But we also want the difference between any two code words to be that D of C to be as large as possible so that you can correct as many as possible errors. Well, as I said, you're asking for too much. These requirements are pulling in different directions. So we then have a constrained combinatorial optimization problem. With that being said, what do coding theorists want to do? We would like to describe a code which achieves, if you fix two of those variables, or two of the values n and m, you'd like to optimize d, the distance. But if you fix q, which is the field, and n and d, so in other words, the length and the distance, you also would like to know how many messages you can send. In doing that, you're optimizing the problem, and you're trying to find the best possible code that you can send. With this being told, for the likes of you who are in the audience, I'd like to just quickly tell you that, for example, suppose what we're doing here is we take 0 and 1 as part of a binary system, and you can add them. And as you can see here, what we are doing here, this 1, when we added with 1, we got a 0, which is that operation that I told you already before. And when one does that, one has a field, and in this case, this field is a field of 0 and 1s only. What happens is we are able to basically compute the sum of two words and in turn have a new word. This is a property called closure. And what more, if you have that, we should be able to decode a code. And if we have such, we can also make use of linear algebra to be able to tell us what a basis of the code might be. And this U1, U2, U3, and U4 is exactly a set of linear combinations over the field of two elements, which then one could use to encode mathematically the message. And if we take this as a basis, we can write any word in this way. Look, X, first coordinate, second, third, and fourth, and then we can write as 1 with first, 0 with second, 1 with third, and 1 with fourth. And you can see that 1, 0, 1, 1 is part of the message. What did we do here? We added these three values as redundancy. In other words, to protect the information. So having done that, one then may think of the idea of what is called the generator matrix to allow us to sort of encode that message and pass the message through an encoding and to be able to send it. Once one does that, one is also able to then ask, suppose this is what you have received. What likely was sent? So with that, one can then find what is called the parity check matrix and decode the message that was sent. So we use this matrix. If you do the product of this vector with the matrix and it's 0, then you have a code word. If you have these different from 0, then there must have been an error. And this tells us exactly where the error could have occurred. Let us just try one case. Suppose you receive this message, which is what we had. When you do the multiplication of this, at S you get that, which is different from 0. And then what it means is that an error has occurred. And we know exactly where this error has taken place. If you go here, you will realize that this second row contains 0, 1, 0. Therefore, the error has occurred in the second row, as we said here. And we can definitely find the entry of the vector where the error has taken place. And this would have been then this position here, which is precisely this. And you can see that this part here is protected. This is what you had to have sent. Well, then, so much about mathematics. Marcus du Sautoy said, mathematics has a beauty and romance. It is not a boring place to be, the mathematical world. It is an extraordinary place. It is worth spending time there. And I hope I'm living up to my promises of telling you what this is. Well, what is a group? Group is not an association of your friends and family, but in this case is an algebraic structure. And this algebraic structure is such that it obeys certain operations. And this operation will be a binary operation and satisfies these three properties, G2, G3, G4, well, including G1, that is what one calls a group. And the group will play a role here because the moment you send a message, and if that message is distorted, it means something has gone wrong, something got permuted by an outer object. The group is doing that permutation for you. And that's where the algebra comes in. And the automorphism group of a code is simply a set that maps the code to itself. It preserves it, keeps it together, does not change it. Now, with that being done, you would ask, what more structures have you used to work with? We have worked with graphs, we've worked with codes, and we've done a process called decoding. Now, there is the notion of a graph is that of, as described here, set of vertices and set of edges, and this is basically a subset of the vertex set of cardinality 2, and we know what is called a valency, which is also the degree of a vertex, the number of edges that contain a vertex. There is what is called a regular graph and a special case of what is called a strongly irregular graph, which is what I have worked on most. You would ask, why are you doing this? It's because I worked on this and I needed to have said to you a little bit of the work that I have done. And this is the opportunity that I have to tell you of the things that I have worked on. The adjacency matrix of a graph then will tell you when two vertices are adjacent and when they are not. So this is an idea of what a strongly irregular graph is. This is what is called the Peterson graph. Now, with this, the idea is if you have a set that you're calling omega, which has n objects, and you find two-element subsets of that set, you can then create a strongly irregular graph, which we call the triangular graph, which has parameters as they are here, and these parameters came as a consequence of the fact that I said that a strongly irregular graph has these parameters. With that being given to you, you then can find the matrix associated to that graph, which is the adjacency matrix, which you will get by simply noticing that this and that share nothing, but 1 and 3 share a 1, so you put a 1. 1 and 4, 1, 4, shares a 1 with 1, 2, then you put a 1. 1, 5 shares a 1 with 1, 2, you put a 1. 2, 3 shares a 2, you put a 1. But 2, 4 shares a 2, you put a 1. But if you come to 3, 4, for example, shares nothing here, you put a 0, and in that way you can make that matrix. By so doing, then you can find the code associated to this matrix, which means which type of code. In this case, we're claiming that we want to find a binary code, so a code defined over a set of two elements, 0 and 1. So the matrix associated to that code would be this, and this code is one with parameters. In other words, the length is n, there is 6 to the dimension, and it corrects d minus 1 over 2, remember, which then means 3 minus 1 over 2. It corrects one error. So if one error occurs, this code has the ability to decode it. So looking at the idea of a group then, well, there is a particular family of groups called alternating groups from which one can construct codes But in this special case, we're using the combinatoric approach. So then, if we have n choose 2 elements, and the k is n minus 2, and the distance is 2 times n minus 2. So basically, you can correct precisely 2 times n minus 2 minus 1 divide over 2, and you take the integer part of that. That's going to be the error correcting capability. The dual of a code is just a set of all orthogonal vectors to the code. And the parameters of this code are such that n is n choose 2, and n choose 2 minus n plus 2 is k, and this code, which is the dual, corrects only one single error. And the idea is that the automorphism group of that code is the set of permutations of the coordinates, which is the symmetric group Sn if n is not 6, and is the alternating group A8 if n is 6. With this, I've sort of given you an idea of what Professor Senkubuka told you, that I also have worked on what is called permutation decoding. Let me not bore you with the idea of what a permutation decoding is. I'll just, in summary, tell you what it does. What you're trying to do, you're trying to have two sets. Basically, one called the information set, in other words, where your message is, and the other called check set, in other words, the redundancy. So you're going to construct this matrix and then ask yourself, if an error occurred, what is the likelihood that I can move that error from the information set to the check set? That's basically what we're doing here. Well, with that, and the mathematics is long, I'm not going to tell you most of the details. I'm simply going to skim through them and tell you that an algorithm can be designed to perform this, and this algorithm is what we call the PD set. So, and then there is also the idea of what is the minimum size of a PD set, and this is calculated by using simply these connections over here. With this having said, the question then would be, what families of graphs would provide you for codes that have permutation decoding sets? Triangular graphs, whose example is the one I have just given you, the 1063, is one such case. The square lattice graphs, and there are many more. Now, what we have discussed until now is the idea of a point-to-point communication. What happens? Is that all that we know? That's definitely not the case. How about this? You have a point-to-point communication is me talking to someone, or me transferring information to some other place. And network coding, on the other hand, is one or more sources transmitting to one or more receivers over a network. As you can see, the sources are labeled S1 up to Sn, and the receivers R1, R2, up to Rm. And this is what happens in cellular networks, in distributed storage, many people putting information on the cloud and being stored. Facebook is storing because in 20, 30 years' time wants us to go back and still find what we have stored and be legitimate of what we have left there. And then there is also streaming. As we speak now, this is being streamed. So we want family members or colleagues to go through this at a later stage, and this is only possible through communication theory. With this then, how does one do that? There is then the idea of multicast model, where again, we help ourselves with the idea of graphs, where we have one source that sends the messages to multiple ends called sink. And then the idea is to correct those errors, maximizing the rate, in other words, the number of messages transmitted per single user of the network. And in here, it's where the connection with computer science also comes in. Well, what happens? I said a few words about cryptography, and the whole world is thinking, oh boy, a quantum computer is going to be built. If quantum computer is built, Peter Shor tells us the RSA and the elliptic curve crypto system will collapse. What will survive? Coding theory will. And why would it? Because the nearest decoding problem is NP complete. And therefore, we will not be able to find a solution, even if we have a quantum computer. So we are, to some extent, safe. Now, the question that you would pose, because the aim of the lecture was to say error-free communication, then you would ask, which codes get very close to that channel limit, to not having errors? Okay, well, cell phone companies are now determined to roll out 5G. There's no way we will convince them otherwise. 3G and 4G are a thing of the past. 5G is coming along. How does it come? Well, that's thanks to the idea of what is called low-density parity check codes. And these are the best performers. They were once theoretically designed for theoretical use. They have now entered the practical world. And now, more than that, there is a second generation which is called polar codes. Although they perform worse than LPDC codes, they are filling the gap slowly. And in fact, 5G phone companies are using both polar and LPDC. There is also what is called turbo codes. And what more then? Well, this is sort of the hierarchy in which I have discussed things with you. We started by the idea of coding theory, error communication, in other words, error correction and error decoding, and we have a channel. And then we looked at some algebra by looking at linear codes, and the implications that come off that, we looked at the 743 code, which is a Hamming code, and there are many others that one can get one's hand into. But I just thought I should give you this idea so that you have some flair of what is happening. Well, why did I say crypto, RSA, will not survive quantum computers, but coding theory will? Well, suppose what you have is an input which is an R by N matrix H, which you've seen me calculating with when I did that W times H, right? So now, suppose that is given to you over a field of two elements. 0, 1 are the objects that you're using, and you have a binary vector S in that field with length R and an integer t greater than 0. The question is there a binary word in the set of words, not in the set of messages, of weight smaller than t? Remember that our code is t error correcting. In other words, t is distance minus 1 divided by 2, and take the integer part. Is there such? And if such exists, it should satisfy that S, it is H times X transpose. Well, this is a problem that has already taken its toll into the mathematics brains, and it's a problem which is NP complete. Well then, let me end by saying this quote by Henri Poincaré: "The mathematician does not study pure mathematics because it is useful. He studies it because he delights in it. And he delights in it because it is beautiful." In this, I then would like to thank you for your patience. And as I said initially, I hope that this has lived up to the expectations. Thank you very much.
Thank you very much, Professor Rodrigues. For me, what really stood out is taking the complex theory of coding and getting that to non-mathematicians and bringing it back to everyday application. So next time you take that 5G call, there's a lot more happening in the background. I won't be able to explain exactly what it was, but I do appreciate the mathematical basis of it. think, having said that slightly flippantly, I think it's also an echo, and it sort of reflects the University of Pretoria's larger way of thinking around crossing boundaries, relevance, impact, and the contribution of the basic sciences to many of the applied problems that we have. So when we talk about transdisciplinary impact, it's easy to overlook the contribution of the basic sciences, chemistry, physics, mathematics. And this is one of those examples which I'm proud and will remember in future presentations when we think about exactly how the University of Pretoria does that. I might have to come back for a few refreshers on some of your slides, but I do see the example. Winding up our event this evening, I'd need to do a few words of thanks. First, Professor Singobuge, thank you very much for your eloquent introduction. I imagine in your role there's quite a few of these, and I really appreciate the effort and personal touch that have gone into this one. Thank you very much for that. You've already mentioned the contribution of Mrs. Veronica Rodrigues and Bevanildo. Also from the faculty side, I'd like to reiterate and say we are acutely aware that the academic endeavor and the academic project knows no boundaries, knows no timelines, and sometimes inspiration strikes at odd times. That does mean that it can be hard on family life. I really appreciate the support and the contribution you've made to get Professor Rodrigues where he is today. An event like this doesn't happen without quite a lot of people contributing. So first of all, thank you very much to Pure for catering. I think any of you that's been to an event with Pure Catering, it might be one of the reasons why you're here. Louis Clute Productions. Louis, I can't remember how many of these we've done together, but again, thank you very much. And then particular thanks to Marie Venter and Laurel September from the Department of Mathematics and Applied Mathematics. That's Laurel, and Marie is from my office in communication supporting these events. I'd also like to extend a welcome to the actual department. Professor Mike Chapwanya, acting head of department, and then Professor Mapundi Banda, who's on not study leave, but visiting some collaborators. The sort of work that you see in front of you that we've had presented today, that doesn't arise by itself. There's an ecosystem of peers, of fellow academics, the people with whom you change the coffee into theorems together with. You don't do that by yourself. The ones that help you navigate the crocodiles and the landmines. It doesn't happen by yourself. So thank you very much for that sort of department which you've created. It's actually not just yourself, it's a whole series of heads of departments, it's a whole community of academics that allow that to happen. I'm deeply thankful for it, and I recognize its uniqueness. This department is one to be reckoned with. It's one that is known for its excellence in teaching. It's also one that's known for the depth of its research and its impact. So thank you very much for that. And again, it's not just directed at you, but to all the other mathematics colleagues here, maybe ones online. Thank you very much. That brings us to the end of our festivities this evening. I ask you to please stand as the procession leaves the hall, and thereafter, please join us for some refreshments outside. Thank you very much.
Gaudiamus igitur